Good morning, everyone. Myself, Yash Vyas. I am a student of International Institute of Professional Studies, DAVV. Today, I am going to present the solution of assignment number 2 assigned by Professor Dr. Saligram Prajapat sir. The first thing which we have to do is we have to write the code for the root finding method using bisection method, Regula-Falsi method, secant, Newton, and the fixed point iteration method to find the roots. The first bisection method. In this code, we will firstly import the NumPy module. After that, we will create the function bisection in which we will be taking the value of FAB and tolerance E, which we will be taking is 1E minus 6, and the maximum number of iteration that will be 100. After that, we will check the condition for the bisection method, and if it not matches the condition, then we return the value of the roots does not exist in the interval a and b, and if it doesn't match, then we will start a for loop from the I to max iteration, I is equals to 0 max iteration, where we will be computing the value of c, which is a plus b divided by 2, and then we will be checking for the absolute value of the function f of c and compare it with tolerance. If it is less than tolerance, then we will return c and the iteration number as the root is equal to c, or else we will check for the condition of which will be the next value of a and b using the f of c into f of a. After that, we will assign the new value of a or b, and then we will return the value of a and b divided by 2. After that, we will use a lambda function to and the create the values and the for create the function, and after that we will be calling the roots and number of iteration from the bisection method and print them as the answer. Now the second method is Regula-Falsi method. In this, we will be creating a function named Regula-Falsi, taking the value of function f of x, a, b, tolerance, and the maximum iteration, that is 100. Then check the condition for whether the roots lie between a or b or not. And after that, we will start the loop from I is equals to 1 to the number of maximum iteration. After that, we will compute the value of c, which you can see from the formula. After that, we will check the condition for the stopping condition, that is absolute f of c less than tolerance. If it's come, then we will return the value of c and I plus 1, else we will return the value of that, and after that we will update the value of a and b. Now the third method is secant method. In this method, we will create the function secant, where we will be taking input as f of x, x0, x1, tolerance, and the maximum number of iteration. Here we have taken tolerance and maximum number of iteration as a default argument. After that, we will create a loop from I is equals to max iteration and assign the value of f of x0 variable and f of x1 by using the f of 0, x0 and f of x1. After that, we will check the condition of whether the roots are between these or not using the absolute f of x1 minus f of x2 is less than the tolerance. After that, if the condition fails, then we will raise the zero division error and demonstrate it as 0. Denominator is equal to 0. Then we will update the secant formula using x2 is equals to x1 minus f of x1 into fx1 into x1 minus x0 divided by fx1 minus fx0, and then we will check the condition whether the roots is find or not using the absolute value of x2 minus x1 is less than tolerance. If the condition match, then we will return the value of x2, which is our root, else we will replace the value of A is equals to B and B is equals to C. And after that we will continue until we reach the max iteration or the condition or the finding condition matches. After that we will return the value of x1 and the maximum number of iterations. After that, in this we are imported the max module, create the function using the lambda function f, and after that we have take here call the secant method and put the values return value in roots and iterations and then print it. The fourth method is the Newton-Raphson method. In this, we have created the function Newton where we will be taking the values like f, d, f, x0 and tolerance and maximum no iteration. We will assign x is equals to x0. Then we create a loop from I is equals to 1 to maximum iteration where f of x is equals to f of fx, and then we will check the condition of whether the root is here or not by using the absolute value of f of x is less than tolerance. Then we will return x comma I. After that we will find the value of df x using the function df, and then we will check the value of absolute value of df. If it is less than the 1 e minus 12, then we will write divide by 0 error, else or else we will compute the value of new x that is equal to x minus f of x divided by dfx. After that we will be return the value of x and the maximum number of iteration if any of these stopping condition doesn't hit. After that here we have do the same thing. We have created the function, we have created the f or df of x, and then we will have call the Newton's method and print the roots. Now the fifth method is fixed point. In this gx0 and tolerance and its maximum iteration is the input, and x is equals to x0, the history is equals to x bracket, and we will create a loop from I is equals to 1 to 0. Then we will generate the new value x new is equals to gx, the history dot append x new. Then we will check for the condition of the tolerance stopping condition, which you can see here in the if statement. After, if the stopping condition doesn't match, we will create the new value of x. We will assign the new value of x as the x, and then we will return the values. And then here we can see that we have created the function f of x, g of x, and we have called the function. After that we have shown the maximum iteration printed true. Now the second question is the Lagrange is the interpolation techniques code. Here we will be talking about the following methods which we have written here. The first is Lagrange's interpolation. We firstly import the NumPy module, then we create the function Lagrange's x point and y points, comma x input. Then n is equals to len of x points. The result is equals to 0 assigned for I to n, I is equals to 1 to n. We will compute the value of li, and after that we will create another loop for j is in range to n. So j is less than not equal to I, then li is equal to li into the following function which you can see here. After that we will we will update the result value by the y point I into li, and then return the value of result. And here we have created the data using NumPy module, and after that we have called the Lagrange's function and then print its value. Now the second method is Hermite method, in which we firstly import the NumPy module, then create the Hermite function and take the following inputs x point, y point, d, y points, and x. Then initialize the value of n is equals to ln x pt. Then build the divided difference table and duplicate x values for Hermite method. After that we will initialize the value of q and z that is np dot repeat x point comma 2 and np dot zeros x into 2 into n comma 2 into n. After that, we will be calling a loop from I is equals to 1 to n, where we will be changing the values of q tables, where you can see it is the q2 into I comma 0 is equals to y pt I y pt I and y dy pi point I, and you can see the following. After that, we will check the condition for I is equals to 0. If it matches, then q2 into I comma 1 is equals to the following function, which you can following equation, which you can see here. After that, we will create a loop from j is equals to 2 to 2 into n, and our inner function for I is equals to 1 in range to j comma 2 comma into n. In this, we will be computing the value of qij using the formula. After that, we will be return the value of result, comma. We will assign the value of result, comma product, that will be q00 comma 1, and then create a loop from I is equals to 1 to 2 into n, and product is equals to x into product into x minus z I minus 1, and result is equals to q I comma I into product, and then we will return the result for the Hermite method, interpolation method. Now the third method is divide difference table. We will import the numpy module, then create the function divide difference table x comma y, then initialize the value of n and f using the len function and np dot zeros n comma n. After that, we will create the initialize the value of f of 0, where we will be uh, zeroth order difference for equals to all the y values, which we will be taking in as input. After that, we will create a loop from j is equals to 1 to n, and loop for I is equals to 1 to n minus j, and then f of ij is equals to this, you can see in the equation, and then return the value of f. Then we will create the Newton interpolation using taking the value of x comma y comma wells, and f is equals to, here f divide difference table is called, and after that n is equal n comma result comma product is equals to len x comma f of 0 comma 1, and after that we will create a loop from I is equals to 1 to n, and here we will be computing the value of product and the result using the f of 0 comma I into product. After that, we will return the answer from the Newton interpolation method, and here we have created the value of x and y using numpy, and after that we have called the Newton interpolation, which internally called the dividend difference table. Now we have to fourth method, the forward and backward difference table. We import the numpy module, then we create the function forward difference, take the value of y, then we initialize the n using the ln y, and table is equals to np dot zeros and comma n, and after that we create initialize the value of first row using the y value. After that we use nested loop for j is equals to 1 to n and I is equals to n minus j, and here we calculate the compute the value of I comma j table using the following uh, expression. After that, we return the table, and then we repeat the same process for the backward interpolation. Just here, the only change in this, we have the inner loop from I is equals to for the inner loop starts from j comma n, range of j comma n, and the equation is slightly different, which you can see here. After that, we create the y value using the numpy module, and call the forward difference table and backward difference table function, and print their value after that. Now the fifth method is Newton interpolation method. In this, we will firstly create Newton forward table by calling the from it the previous function. After that, we will assign the value of s is equals to x minus x0 divided by h. Then n comma result value assigned as ln y comma y0. Then s product is equals to 1, and then we will create a loop from k is equals to 1 to n, and s product is equals to s minus k minus 1, and result is equals to this. After that, we will return the result and then create the new function is Newton backward. In this, we will create taking the Newton backward table from the previous question and then assigning the value of s and result and s product. Then creating a loop from k is equals to 1 to n and compute the value of s product and result. And in the end, after the end of loop, we return the value of result. Now the third question is numerical differentiation. The methods are interpolation based and finite difference. The first method is numerical difference method, where we will create the numpy module, where input the numpy module, create a Lagrange derivative function for the interpolation taking x and y values, x point, y points, and x value which we have to find. Then assign the value of n and the derivative using this you can see. Then create a loop from I is equals to 1 to n and assign the value of dl is equals to 0. Then after that, for k in range n, we will check the condition firstly that k is not equals to I. Then we will create a initialize a variable product to is equals to 1. Then for j is equals in range to n, if the j is not equals to I and j is not equals to k, we will compute the value of new product which you can see here from this. After the loop's end, we will compute the value of dl using the product dl plus product divided by x point I minus x point k. After that, we will compute the final value of a derivative that is equals to derivative plus y point I into dl and then return the value. After that, in the second part, which is the finite difference methods, we have used the all the uh, we have to create the forward and backward difference and central difference table, which we have already which we can already use a one line function. That is, we can directly return the value of f of x plus h minus f of x divided by h, f of x minus f of x minus h divided by h, and f of x plus h minus f of x minus h divided by 2h. Now the fourth question, we have a numerical quadrature and we have to write the code for Newton-Cotes formula and Gaussian quadrature. The first one we will be telling about the Newton-Cotes formula. In this, we firstly create the trapezoidal function. We will taking the value of f a b and the number of maximum values which we can use for this function, that is 100. Then we will initialize the value of h using b minus a by n. Then the value of x s and p dot line space a comma b comma n plus 1 and y using f of x. Then we will return the value of h into y 0 divided by 2 plus sp sum y 0 to y n minus y index 0 to y index minus 1, which is the last two index, and after that we will divide the y minus 1 index by 2. Now in the Secant method, for the Stefan's method, Stefan's 1 by 3 method, we will taking input as f of x, a, b, and the maximum number of iterations, maximum number of values which can be assigned, that is 100. Firstly, we check the number of values for the solution. If it is not divisible by 2, then we if it's not divisible by 2, then we just exit from the loop and we doesn't do anything, since the Stephen 1 by 3 method is only for the value of n, which numbers of n which are divisible by 2. After that, we will compute the value of h is equals to b minus a divided by 2, and the value of compute the value of x, that is np dot line space a comma b comma n plus 1, and to compute the value of y that equals to f of x. Then we will return the result from the Stephen method using the following expression: h by divide by 3 into y0 plus y minus index 1 n minus 1, then 4 into np dot sum, where the values will be evens using this method of slicing 1 is to minus 1, 1 to minus 1 at the steps of 2, and 2 into np dot sum, where the numbers are odd, using the y2 starting from 2 to minus 2 index at the steps of 2. I am sorry, we will divide the odd numbers using this by 4, and that is our result for the Stephen's method. Now for the Gaussian Legendre Quadrature, we will create the function Gaussian Legendre and input the value of f of x, a, b, and n, that is equals to 5. We are for the 5 point. Then we will initialize the value of node and weight using np.polynomial.legendre.Gaussian n, which directly gives the Gaussian formula. Points you by taking input as the number of points we have to use for the Gaussian formula. After that, we will transform minus 1 comma 1 to a comma b using t is equals to 0.5 into a b minus a into node plus 0.5 into a b plus a. Then we will return the value of the Gaussian Legendre quadrature using the following expression: zero point 0.5 into b minus a into np dot dot to weight comma f dot t. Then here we have created the expression for the Gaussian using the lambda function, and then in a call for the lambda function, and after that we have called the trapezoidal and the Gaussian formula to illustrate the answer of the following for the same function points. Now the question number 5 has started. In this we have to solve for the system of simultaneous equation using the three methods: Gaussian elimination, Jacobi iteration, and Gaussian slider. The first method is Gaussian elimination. In this, we will take the input numpy module, create the function Gaussian elimination, take the value of a comma b, then initialize the value of n. Then we will initialize the argument matrix using the following expression. Then we will do the forward elimination using the loop from k is equals to 1 to n. Then create the pivot partial pivoting using maximum number of row is equals to you find the maximum number of row using this expression, and then assign the value of ab comma n comma k comma bracket k comma maximum rows is equals to ab maximum row comma k. It will give the pivot element values. After that, we will create another loop from I is equals to k plus 1 to n, where we will compute the value of vectors and ab I comma k values. After doing that, we have completed our forward elimination process. Now we will start with the backward substitution, where we will start with x is equals to np dot zeros, and then for I is in range n minus 1 to I1 at the steps of minus 1. After that, uh, we will compute the value of xi using the following expression and then return it. Then we have created a matrix A using NumPy and created another vector B using NumPy. After that, we have called the Gaussian elimination method then print its value. Now in the Jacobi's method, we have taken input as a, comma b, comma tolerance, comma the maximum number of iteration, initialize the value of n, comma x matrix. Then we have created a loop from till the maximum number of iteration. Then compute the value of new x using np.0. Then create a loop from I is equals to 1 0 to n, where we will be computing the value of sum using this expression, where the after that we will compute the value of x underscore new using this expression, and then we will check the conditions for the tolerance using this expression, and if the condition hit, then we will return the new value as our answer. Else we will continue it, we will assign x new to new value and return the x new after the completion of the all the loops. Now in Gaussian slider method, we will take input as a, b, tolerance e, and maximum number of tolerance 1 minus e minus 6, and the maximum number of iteration 100, and then compute the value of nx. Then create a loop from 0 to maximum iteration. Then assign the value of x old using the x dot copy. Then create a loop from I is equals to 0 to n. Compute the value of x using the new values of the x and y and all, and then we will compute the value of xi using the updated x, and then we will check the condition for the conversion. If it matches, then we will return the value of x as our answer, else we will wait until all the loops end. After that we will return the value of current x, and then after that here in this code we have created an array a and b, and then call both the method Jacobis and Gaussian sliders and print their output. Now the sixth question, approximation method, like a least square method and ordinal polynomial approximation. Now in the method we will first take the least square approximation, then create the first function of least square approximation taking input as x comma y comma degree. Build the Worthman matrix using by assigning value of a, create the normal equation using this following expression and return its value. After that, we will create an array x and array y using numpy, and then create the c, which is our answer, using the least square approximation function, and then print the values as the result. Now in the orthogonal polynomial or Legenders, we will create the function Legendre approximation, input as f of x and terms and x points. Then for np dot polynomial dot Legendre, import the leg fit and leverage. After that we will map x points to 0 minus 1 comma 1 using the following expressions. Then we will compute the value of y points using f of x point fits. After that we will config c is equals to Lagrange fit, then the values which you can see expression, and after computing this all values we will return the value of coefficients, which is our answer. Now the seventh question is ordinal differential equation, where we will be showing the following methods. First, in the Euler method, we create the function Euler, input f of x, x0, y0, h, and x. When we compute the value of x as input argument, arrange x0, comma xn plus h, comma h. Then we compute the value of y as np dot zeros. Then compute the value of y as and equals to y0. Then we will find the value for i in range 1 to len x, and then compute the value of s y s I. After that we will return the value of xs and xs, which is our answer. Now in the Runge-Kutta method, we will take input as f of x, x0, y0, h, and n. Then we will initialize the value of xs, ys, and ys0 equals to y0. Then for range, or for I in range 1 to n of xs, we will compute the value of x comma y. We will assign the value of x comma y with the previous values, and then we'll compute the value of k1, k2, k3, k4, and yi using the following equations. And after the end of this loop, we will return the value of xs and ys, which is our table generated by this. Now in the end, we have used the Lagrange's function, a lambda function, to create the differential equation, and then we have called the Runge-Kutta and Euler's method and show their result. Now the next method is pickle method, where we will creating the pickle function, import the value of x expression x, y, y0 value, and the n iterations, which is equal to 3. Then we will assign the value of x sim and y sim. We're using the symbol x comma y. Then we will assign the value of approx, which is equal to y0 for dash value. Then we will create a root till the n iteration. Then integrate is equals to f of expression dot sub y slash sub approx and approximate, and in compute the value of approx. After computing the approx value, we will simplify the approx using the simplify function, and then in the end we will return the value of approximation, which is our answer. Now in the Taylor series, we will be taking input as f of x, x0, y0, h, xn, or in order 4. We compute the value of x comma y, which equal to x0, y0. Then we compute the value of x comma y s equals to x comma y. Then we will create a while loop from x until the x is less than xn minus e 1e in minus 10, which you can say is the R tolerance also. Then we will approximate the derivative numerical using the dy functions, which we have created here. After that, uh, we will create another loop from k is equals to 1 to order and compute the value of dy using the following expression. After the end of this loop, we will compute the value of y and using the expression, and the compute the value of x using this expression. After that, we will return the xs and xys value, which is our answer for the Taylor series table.